Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at how you can write your own balanced redox reactions. So one of the first things to remember about redox reactions is that at their heart, you're looking at electrons being transferred. And this means that you balance and construct a redox reaction very differently than you would any other type. So one of the first things we need to figure out is that we don't need to just balance the number of atoms and charges, but we also need to balance the number of electrons being transferred as well. We need to make sure that we're losing as many electrons as we're gaining. And one of the easiest ways to figure out how many electrons each oxidation and reduction reaction requires is to balance them separately. So we're going to go ahead and look at a half reaction for the oxidation and a half reaction for the reduction, and then add them together at the end with the right number of electrons. And we're going to do this by following a fairly set pattern. So first thing we're going to do is write the unbalanced reaction. And one of the big differences in between redox reactions and other kinds is there may be some atoms that we aren't necessarily accounting for. Principally things like solvent, which comes and goes. So we're going to mostly have our heteroatoms, so things that aren't oxygen and hydrogen. So the first thing we're going to want to do is, with those species, figuring out which atoms are oxidized and which are reduced, and correspondingly write our unbalanced half reactions. And then we're going to balance both of our half reactions for everything except for oxygen and hydrogen. Again, making sure all of our carbon, nitrogen, fluorine, everything else is balanced. Then we're going to add any water to the system by adding we're going to balance oxygen by adding water to the side with less oxygen atoms. We can, once we've done that, we've added some extra hydrogen. So we're going to need to balance hydrogen by adding protons to the side with less hydrogen atoms. Next, we can then add electrons to the more positive side to make sure that our charge is balanced. So we have equal charge on the left as on the right. Then big thing that we have to keep in mind here is the oxidation reaction may have different numbers of electrons than the reduction. So we need to multiply both sides by suitable factors until both have the same number of electrons. Then with equal number of electrons on both our reduction and oxidation reaction, we can combine our two reactions together and then just make sure that the resulting equation is fully balanced with the right number of atoms and charge on both sides. So this is more or less just making sure you did the previous 8 steps correctly. So let's go ahead and look at a fairly biologically relevant reaction. So turns out a lot of microbes essentially power themselves not through classic respiration metabolism, but they can instead reduce nitrate into nitrous oxide. And they do so by getting the electrons from any free iron in solution, turning iron 2 into iron 3. So this is actually used to power a fair number of aquatic microbes. So specifically, this happens a lot in areas without a lot of oxygen. So think marshes, swamps, and tidelands, as well as some oceanic currents, which tend to be very iron limited. So again, our two half reactions is on the nitrogen side, nitrate is reduced to nitrous oxide, and iron is oxidized into iron 3 plus. So now we can go ahead and we have both of our reactions. We're going to make sure that the heteroatoms are balanced. So I have the same number of nitrogens on both sides, so we're good, and the same number of iron atoms on both sides, so we're good. Next, we're going to balance the oxygen. So on the iron case, this is super easy. There is none. On the nitrate case, you'll notice that the right-hand side is short 2 oxygen atoms. So we're going to add 2 water molecules to the products of the nitrate reaction. Next, we need to balance hydrogen. Again, on the right hand, iron, that's easy. There are none. For the left-hand side, this is a little trickier. As we have 4 hydrogen atoms on the right-hand side, but no hydrogen atoms on the left. So we're going to need to add 4 protons to balance everybody out. Next up is charge. So let's go ahead and look at the nitrate reaction. The products are neutral, but if we add up the charges on the left-hand side, we have a 3 plus. Well, then we could use 3 extra electrons to make this neutral. On the iron side, we have a 2 plus and a 3 plus. So we need to add an electron to the product side to make sure that this is 2 plus and so is the as well as the left. So this gives us 2 balanced half reactions. So then the next step is to make sure that both of these reactions have the same number of electrons. So I have 3 on the left and 1 on the right. So I need to multiply this whole reaction by 3 in order to be gaining 3 electrons on the left and losing 3 electrons on the right. So now we should be ready to add our 2 reactions together. So one of the big things to look for is what cancels out. So there's only one species that occurs for both reactions, and that's the electrons. So this is going to be pretty easy. So the electrons on the products cancel out with the electrons on the reactants. So then our reactants become nitrate plus iron, 2 plus those 4 free protons. That's everything on the left, and on the right, we have nitrogen nitrogen monoxide plus those 3 iron 3 plus ions plus 2 water molecules. So at this point, it's a good practice to look through and make sure that we don't have any species that occur on both sides. If you do, make sure you cancel them out, because at that point, they're just spectators to the main reaction. So everything looks pretty good here. We now have the balanced reaction for how this occurs in nature. However, it turns out we don't always have these free protons available. Plenty of solutions don't have extra protons. Most notably, this happens in basic solutions. So in basic solutions, you're way more likely to see hydroxide than you are to see a proton. So for basic solutions, we can modify the reaction by adding 2 additional steps. The first one is going to be adding enough hydroxide to both sides to neutralize any H+. So what this does is it turns any H+ into a water molecule. Then, since we've generated extra water, make sure that we cancel out any water that appears on both sides of our new reaction equation. So let's go ahead and look at this for our nitrate system. So we now have a balanced system for what we call acidic conditions, where we have protons, which again define an acid. So if I've got 4 protons on the left and no protons on the right, I need to cancel these out by adding 4 hydroxides to both sides. So I add 4 hydroxides to the left and 4 hydroxides to the right. Here, my hydroxide and my protons will react to make water. Ta-da! So I make 4 water molecules on the reactant side, and I introduce the 4 hydroxides to the right. That's the biggest deviation from our original equation. However, you may notice that we already had water on our product side. So I need to essentially cancel out any redundant waters. So I add 4 waters, but I get 2 back, which means net equation, I only end up adding 2 waters. So we can use this to generate a balanced equation. So some of the big take-home points from these redox reactions is that when you're looking at redox reactions, it's really easy to miss a lot of molecules that tend to come and go very easily in aqueous systems. Most notably, protons, water, and hydroxide. And in addition, we've got a lot of charges floating around very quickly. So we again take things a little slow. It takes a little longer to balance a redox reaction than a normal reaction, because we have to do the half reactions, make sure our charges are in line and we're transferring the right number of electrons, and then get our spectators right, make sure everything cancels out, and be very aware of whether it's acidic or basic. This will change a lot of the environment. Next time, we're going to do a quick deviation into looking at one of the side products of a lot of our acid-base or redox reactions. What happens when I make gas? Until then, take care.